Okay, today guys, we're going to talk about 4.5 and how derivatives affect shapes of graphs. This is like part 2. So, oops, let me go ahead and clean that up. So part 2, derivatives. Okay, so we're going to do an 8. Some of them are very simplistic steps, but I'm going to say that there's 8 steps that we're going to go over. So this is nothing new than 4.3. The only difference is there's just going to be a little bit more asked of you, and then we'll sketch a graph based on that. Okay, so let me give you, it's going to say graph using the 8 steps. Now, listed. Okay, and the problem we'll get is f of x equals e to the x over x. So here's the thing. If you're using the online book, it won't have 8 steps. It'll just ask you for certain topics. If you're using the Stewart book, it will show you how to do the 8 steps. So I'm going to teach it from Stewart, and those of you that are using online will just have a little bit less to do. 4.5 is kind of just a little bit cumbersome, but it'll help you get a little bit of understanding. If you guys are using the online, you might want to look at a few from the book as well, just to kind of get some practice with it. The online book doesn't have as many e to the x's or natural logs of x problems, so this will be where you get those from. So the first thing they want, is the domain. So they want to know the domain of the function. So we know the domain is what values you're allowed to use with this function. In general, it's what x is, you know, how far left, how far right, all that stuff. So this should be something you guys already know. We know that we can't plug 0 into this problem, so we're going to say x such that x cannot equal 0. That'll be our domain. Okay. Second thing they want to know are x-intercepts. Oops. X-intercepts. Okay, so if we look at this problem, to find the x-intercept, remember you say that f of x, if you want to find the x-intercepts, you let it equal 0, and that means e to the x over x equals 0. Well, what's the only time that e to the x over x would ever be 0? Is when the numerator is 0, so we're going to come over here, and we're going to set e to the x equal to 0, but e to the x can never be 0 because it's an exponential function. And there's no power that you could ever take it to that would somehow make it 0 all of a sudden. Even if you took it to the power of 0, it'd still be 1. I guess you could do negative infinity, but that's not a real number in terms of what we're working with, in terms of domain. Or I should say you can't plug negative infinity in as an actual number. So we're going to say no x-intercepts. Okay. So now we'll go to step 3, or part 3, I guess you could say. And again, something easy. So again, you guys should not be freaking out about this. F of x equals e to the x. When would this have y-intercepts? Well, remember, in order to find y-intercepts, you let x be 0. So then you would say f of 0 equals e to the 0 over 0. But you can't do that, so there is no y-intercepts as well. So no y-intercepts. Okay, so now we're going to go to the fourth thing. The fourth thing they want to know is vertical asymptotes. Vertical asymptotes, I'm sorry. So vertical asymptotes. So you guys remember from the previous chapter on limits, we could find vertical, or not the previous chapter 3, but from chapter, geez, that was chapter 2. Vertical asymptotes we can find by deciding what values, usually we do it by looking at what values in the denominator could cause the problem to be undefined. So in this particular problem, we know that 0 is a problem. So we let x approach 0 from the right or from the left. And this would become e to the x over x. Well, this would become infinity. And limit as x approaches 0 from the left of e to the x over x would equal negative infinity. And again, you can think about this as you're plugging a number very close to 0 into here. You would get 0.00000001, and e to the 0.0001 is almost 1. 1 divided by something really, really close to 0 becomes infinitely large. And then you could do the same thing with 0 from the left-hand side, plugging negatives in, okay? So we know there is a vertical asymptote x equals 0. So if you were to get infinity or negative infinity for either one of these, you automatically know there's a vertical asymptote. I just did both, but technically the moment you have one, the left-hand side or the right-hand side, you know there was a vertical asymptote. 5. Oh, and also remember that this value, where did I get this value from? Well, I got it from finding usually when the denominator would equal 0, okay? So if it was like x minus 4, then we would have said as x approaches 4 from the left or from the right also, okay? So step 5, you guessed it, horizontal. Okay, so horizontal asymptotes. Now you guys should recall that to find horizontal, you take the limit as x approaches infinity of e to the x over x, and you do the limit as x approaches negative infinity of e to the x over x. This is how we find horizontal asymptotes. So if we plug infinity in, we get infinity over infinity. But now we know L'Hopital's rule says that I could just take the derivative. So I'd have limit as x approaches infinity of e to the x over 1, which is infinity. So far, no horizontal asymptote. Okay, so now we come over here, and if we plug negative infinity in, technically this would become 1 over oops, let me write this. Well, I guess you could think about it like this. It would be 1 over e to the infinity times negative infinity. And again, that's not, you're not actually allowed to plug that in, but that's kind of what happens. Now think about this. E to the infinity is going to be extremely large times negative infinity, which is another extremely large negative number. And two extremely large numbers multiplying times each other is going to be extremely large. So you're going to have 1 divided by an infinitely large negative number. Well, this would become 0, okay? So in this particular case, e to the x over x, as x approaches negative infinity, would actually be 0. Okay. So we have horizontal asymptotes. So we have a horizontal asymptote at y equals, let's see, y equals 0. So that's our horizontal asymptote. So now for part 6, it says we need to find if there's any symmetry. So is there any symmetry? You guys know that find symmetry. Okay. However, you guys know from pre-calc even and odd functions. Okay, that's kind of the main symmetry we're going to look at. So we do f of negative x would equal 1 over e to the x times negative x. This is definitely not equal to negative f of x, so definitely not. And it's definitely not equal to e to the x over x. This would be even, this would be odd. And it's neither of those, it's something different, so no symmetry. Okay, so now we have to go on to step 6 or part 6. Now this is the new stuff. Everything that we've just done was old stuff from previous sections. So now we have to do the new stuff where we have to find the derivative. So they're going to ask us for increasing / decreasing and local min / max. Okay, so what we're going to need for that is f prime of x. So we're going to have the derivative of, well, you know what, let's write f of x first. F of x is equal to e to the x over x. Now you guys take a minute. You guys take a minute, pause the video, and try to find the derivative on your own. So f prime of x equals, so take a minute to do that. All right, so hopefully you guys have done the quotient rule, and you have e to the x times x minus e to the x times the derivative of the denominator, which is 1 over x squared. So if I factor a little, I have e to the x times x minus 1 all over x squared. Okay, so remember, to find your critical numbers, like from 4.3, we're going to have to set the denominator and the numerator equal to 0 and find out when the derivative is 0 or does not exist. So e to the x itself can never equal 0. We talked about that earlier. X minus 1 can equal 0, and x squared can equal 0. So this means x equals 1, and this means x equals 0. However, this is not in the domain of the function. However, it still can be a singularity, but it cannot be a critical number. So our only critical number is x equals 1. Remember, critical numbers have to be in the domain of the original function. And we said all the way back up here, the domain is x cannot be 0. Okay, so now we're going to do our little number line like we're used to. And we're going to use 0 right here. And then I told you some students like to put a little circle around it because it's in singularity. And then we're going to use 1 right here. And now we have to do our test. Okay, so I'm going to do f prime, and this is f prime of x. I'm going to do f prime of -1. I'm going to do f prime of 0.5, and I'm going to do f prime of 2. Okay, so when you do f prime of -1, we come up here, and I'm going to use this right here. Plug -1 into there, we get -2 over a positive. So this will be a negative over a positive. So this will be a negative, right? Then we plug 0.5 in there. So this will be a negative over a positive. So this will still be negative. And then we plug in 2, we get a positive over a positive. So this will now become positive. Okay, so we now have intervals of increasing, intervals of decreasing. We're going to try to decide if there's a local min or a local max or both. Now, I know there can only be one local min or max because there's only one critical number. And remember, critical numbers only occur, local mins or maxes only occur at critical numbers. So we know that there's only one or the other, but there cannot be both. So we'll see what happens with this. Okay. So now try to remember how I talked to you guys about it. This one, you kind of think of this as going downward, but it's still going downward, and now it's going upward. So remember this, kind of like a valley, and then this is just downward, 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 okay? So let's write our increasing interval, and that would be from 1 to infinity. Let's write our decreasing interval. That would be from -infinity to 0, union 0 to infinity. Remember, we can't actually touch 0, so we have to hop over it with our union. And then we know that there's a local min, and the local min is at 1, comma. Now we can go back up here. Oops, we don't need to go way up there. We can use f of x and plug it into the original function. So I'm going to plug 1 into the original function, and I'm going to get e over 1, which is e. So I have 1 comma e. Okay, and then local max, we talked about it. There isn't one. There can't be because we only have one critical number, and we found the local min. Okay, so that's step 7. All right, now you guessed it, step 8. or part 8, is concavity, and points of inflection. Okay, so let's do f double prime of x. So that means we got to come up here. Maybe I should rewrite the original first. So we have f of x is equal to e to the x over x. We have f prime of x is equal to e to the x times, what did we end up getting? X minus 1 over x squared. So now we got to do f double prime. I'm going to be honest with you guys, in general, the second derivative test for concavity is normally the hardest part of the whole problem for most of these, okay? So we're going to have to do the quotient rule with a product rule built into it. So this is going to be a little annoying. So we're going to take the derivative of the numerator, which is e to the x times x minus 1, plus e to the x times the derivative of the numerator, which is 1, times the derivative of x minus 1 is 1. And all of this is times the denominator. So that's the first part of the quotient rule. And remember, this is, if this whole thing is u over v, then this is u prime, this whole thing is u prime, and this is v. So that's all we did, is we did u prime times v. Now we have to do minus the derivative, or let's rewrite the numerator, e to the x, x minus 1, times the derivative of the denominator, which is 2x, all divided by x to the 4th now. So now we have some serious cleanup. Okay, so now we have, let's see, this will be e to the x. You know what, I think I can factor an x minus 1 and an x out. So I'm going to factor out an x minus 1 and an x. So I'm basically taking this x minus 1. No, you know what, I better not cheat like that. Okay, so this will be e to the x times x minus 1 times x squared plus e to the x times x squared minus e to the x. You know what, let's do 2x e to the x, x minus 1, all over x to the 4th. Now you notice that every single term has an x in it, so I can divide by x to all of them. So this will be 1x, or just a 1. This will be x to the 1, and this will be x to the 1, and this will now be x to the 3. So let's do a little bit more cleanup. This will be e to the x times x squared minus e to the x times x. Yeah, plus e to the x minus e to the x minus 2e to the x, 2 e to the x. Okay, all over x cubed. Okay, so let's clean up some more. So let me see here. This right here is an e to the xx, and this is an e to the xx, and this is an e to the xx. They all have an e to the x, so let's factor that out. That's going to be e to the x squared minus x plus x is 2x minus 2 all over x cubed. And all I did, you guys, is I should have actually factored out e to the x from the very beginning. It could have made my life easier, but I didn't notice it. So this now will become e to the x times x squared minus 2x minus 2. For some reason, oh no, this is a plus 2 right here, because when you distribute, that becomes a plus 2. So this will be plus 2 all over x cubed. Okay. Yeah, I should have noticed that e to the x, e to the x, e to the x, e to the x, e to the x. Everybody has e to the x. I should have noticed that. Sorry about that, you guys, but we got there. So we have e to the x, x squared minus 2x plus 2. Now, x squared minus 2x plus 2, either use the quadratic formula, or you could graph it on your calculator and see that it has no x in it. So x squared minus 2x plus 2 will never equal 0. E to the x will never equal 0. So our only hope is x cubed equals 0, so x equals 0. So this is our only second derivative value that will make the problem 0 or undefined. But that's also our singularity. So we're going to draw a number line. We're going to graph our critical numbers and our singularities. Well, we don't have any critical numbers. So this is our f double prime of x. We're just going to use 0. We're going to test to the left and to the right of 0. So we're going to do f double prime of -1 and f double prime of 1. Okay, and again, I'm using this value as my singularity. There is no critical, or not critical numbers, but values that make the derivative, second derivative 0 or undefined. And when I plug -1 in, I should get, let me see, negative. So the bottom will be negative and the numerator will be positive. So we have a positive and a negative, so that'll be negative when you plug that value in. Now when we plug 1 in, we get, let's see, 1 minus 2 plus 2, so we'll get a positive over a positive, which will be positive. So we know that this guy is concave down, and we know this guy is concave up. Okay, so now we're able to look at this and say concave up on the interval from 0 to infinity, concave down on the interval from -infinity to 0, and point of inflection is none, because even though it changed concavity at 0, so even though it changed concavity at 0, technically 0 is a singularity. It's not in the domain of the original function, and a point of inflection you must be able to touch. You have to be able to touch the point of inflection on the graph, so it has to exist, and in this case 0 does not exist as part of this graph. So these are all steps that we would need to do to be able to give a little rough sketch. Okay, so we're just going to do a rough sketch, and that's kind of the idea behind this, is to be able to do a rough sketch. So first thing we know is there's no x and y intercepts, and somehow at 0 it's concave up from 0 to infinity. So I'm thinking it's going to be something like this, and then I'm thinking it's going to be something like this. Now let's just double check. Let's double check right here. So it says that we are increasing. So let me highlight this. We are increasing from 1 to infinity. Okay, so that can't exactly be it, because starting at 1, we have to be increasing. So I'm going to fix this. So I know that I'm concave down, and I know there's an asymptote. So I'm thinking it's going to be something like maybe this. Like that maybe. And then we'll call this starting here at 1. And then, oh, we know this height is E because that's a local minimum, right? So we know that this value here was 1 comma E, that's our local min. Okay, and notice that the graph is concave up from 0 to infinity the entire time. It's not going to come back down. Notice here the graph is concave down from -infinity to 0. It's not going to go back up, yet we were still able to hop over 0 right here because we know that that's a singularity. It's also an asymptote right here. It says x equals 0 is a vertical asymptote, and it says right here y equals 0 is a horizontal asymptote. So we know that we have some asymptotes here, and we know that we have a horizontal asymptote here. Okay, so this is kind of I feel like it's matching all of the things that I needed. Okay, so that would be our first problem, and as you can tell, they take a little bit of time. But they're very, you know, parts 7 and 8 are basically what you were doing in 7.3. So now I want to talk to you guys a little bit about a graph. We'll spend about another 10 minutes on this one, and then we'll call it a day. Okay, so let's say that I have this graph. Okay, and let's say here's -1, here's 2. And let's say we go like this. 1. Then we're going to come back down here. Let me label this for you guys. And then here at 2. Okay. So we have this graph, all right? And this is the graph of f prime. So this is not f of x, this is the graph of f prime. Maybe I should put it over here. So this is the graph of f prime of x, okay? And I would like to know, so below or above is listed use this graph to determine intervals increase/decrease of plain f of x, not f prime, but regular f of x, the function, and local max. Also find where f of x is concave up and concave down, and any points of inflection. Assume f of x is a continuous. You don't have any singularities. Okay. So here's what we got to do. We got to find our intervals of increasing and decreasing. So now look at this. Now normally you have f of x and then you take the derivative of it, and then based on the derivative, you can then tell me where there's intervals of increasing or decreasing. But this time I'm giving you the derivative and I want to know where f of x is increasing or decreasing. So pause the video and see if you could answer these questions without my help. All right, so hopefully you guys got started. Now, if you're really struggling, like you're just looking at it like, I don't even know where to begin, don't feel bad. That's kind of what happens sometimes with derivatives. You don't really think about what you're finding. So let's kind of bring it back. Remember, how did we find out intervals of increasing and decreasing? Well, we did our sign chart and we needed critical numbers, right? We need critical numbers. Oops. So maybe we have one there. I don't know. You know, we need our critical numbers. So we need to first find the critical numbers. And remember, I'd always go and write f prime of x here. And then we'd have to test to the left and to the right. So what was a critical number? Wasn't a critical number when the derivative was equal to 0, right? Or when it was undefined, or DNE. But in this case, it cannot be undefined because this is a continuous function. So that means that we only have to worry about when the derivative is equal to 0. Well, I can tell you right now, the derivative equals 0 right here, and right here, because those are the 3 x-intercepts of the derivative. So that means the derivative is 0 at those locations, okay? So I'm going to use -2, 0, and 4. These are my critical numbers. Right? Because that's when the first derivative is 0, okay? Some people would have said it was right here and right here because that's a local min and max, but that's a local min and max of the first derivative, not of the original function. So we'll talk about that later. So now we're going to test to the left of -2, and to the left of -2, you might say, well, the slopes are positive, but we're not doing that. That's if it was f prime. I mean, that's if it was f of x, and then we would, be looking at the graph of f of x. This is already the graph of the derivative of f of x. So that means that we actually know that the derivative is negative on the left side of 2. So we know the derivative is negative. On the right side of 2, all the way up until 0, notice the derivative is above the x-axis. So doesn't that mean that the derivative is positive? So we know that this is positive. And then now we know this is negative from here to here. Look, these are all below the x-axis. So that means those derivative values must be negative. Okay, and then back to positive past. Okay, so we now can determine increasing intervals are going to be from -2 to 0, union 4 to infinity. And we know this because that's where our first derivative is positive. We know decreasing intervals are from -infinity to -2, union 0 to 4, because that's where our first derivative is negative. Now, anywhere that we change from increasing to decreasing or from decreasing to increasing, we have local mins and maxes. So we have a local min. Okay, so now let's look. Here we were going from decreasing to increasing. So that means that we have a local min at x equals -2. We can't really find the y values because they didn't really tell us the heights. And then we also know decreasing to increasing. So that's a local min at x equals 4. Local max at x equals, now here we're going increasing to decreasing. So that means we have a local max at x equals 0. And that's it. We can't have another one because there's only 3 critical numbers, so there can only be 3 local mins and maxes. Now for concavity, we have to do a second derivative test, f double prime using our number line. Now, where is the second derivative 0? It's wherever the second derivative is 0 or undefined. That would be when the slope of the derivative has a 0 slope. So that would be here and here. So the local mins and maxes of the first derivative are actually, I don't want to call them critical numbers, but their version of the critical numbers for the second derivative. So that means -1 and 2. -1 and 2. And now we're going to do our second derivative test. So to the left of -1, what type of slopes are those? Because remember, the second derivative is the slope of the slopes of f of x, because it's the slopes of the first derivative. So the slope to the left, so we're looking at right here now. So we're looking at right here, the slopes to the left of -1. Those are all positive slopes. They're all increasing. So we're going to come over here and we're going to say these are positive. So that means we have concave up. Now, in between -1 and 2, look at all these slopes. These are all decreasing slopes. These are all in the negative direction. So then we're going to say that this is negative, negative, negative. And then I think you guys get the feel for it. It's positive, positive, positive after that. If we come over here, these are all positive slopes now in this direction. Okay. So we now can say concave up from -infinity to -1, union 2 to infinity, and we can say concave down from -1 to 2. Points of inflection. Now again, we can't say the y value, normally we would. Whenever you change concavity and it's in the domain, that's a point of inflection. So x equals -1, x equals 2 are our 2 points of inflection, okay? So this is how another way you can think about all these times that you're taking the derivative, what does it actually mean for the actual graph? This is a way you could think about it, and you guys can mess with this and try to see if you could come up with a possible graph of this based on our local mins and maxes and our intervals of increasing, decreasing, concavity, and everything like that. Okay, you guys, I gotta end this video before it gets too long, and I will see you in class.